Chemical properties of carbon. Carbon, a non-metallic chemical element with the symbol C, is the basis for group 14 on the periodic table. Its atomic number is 6 and it has 6 protons and 6 neutrons. The electronic configuration of carbon is 1s2, 2s2, 2p2. Carbon is tetravalent, meaning it has 4 electrons available for the formation of covalent chemical bonds. It will not dissolve in or react with water, acids, or most other materials. Knowing the basics, let's now look at some of carbon's chemical properties. Carbon will undergo oxidation to yield carbon dioxide. Consider charcoal, which when burnt in sufficient oxygen will yield carbon dioxide. Burnt in insufficient oxygen, however, it will yield carbon monoxide. When red-hot carbon is treated with steam, carbon monoxide and hydrogen gas will be formed. Carbon will form not only strong C-to-C single bonds as in alkanes such as ethane, but it will also form carbon-to-carbon double bonds in alkenes such as propene. Carbon-to-carbon triple bonds are common in alkynes such as butane. Carbon has the ability to form long chains. Consider polyethylene, the most common plastic, which is made up of a long chain of carbon atoms attached to each other as well as to hydrogen atoms. While many elements such as oxygen, nitrogen, hydrogen, chlorine, or bromine combine as diatomic molecules, carbon can form a cage-like fused ring structure known as fullerene or buckyball. It has a molecular formula of C60. When carbon reacts with an element of similar size and electronegativity, covalent carbide will be produced. When silicon dioxide is treated with an excess of carbon at 2300 K, silicon carbide will be formed. Summary. Carbon is a non-metallic tetravalent element with an atomic number 6. Carbon will become oxide when exposed to excess air and form carbon dioxide, and in insufficient air, carbon monoxide. Carbon can form long chains.
Covalent bonding. Chemical compounds are formed by joining of two or more atoms. When electrons from different atoms interact with one another, a chemical bond is formed. Valence electrons, which are those found in an atom's outermost shell, are the only electrons that will participate in this bonding process. As two atoms approach one another, electrons in the outermost shell of one are repelled by the electrons of the other, while simultaneously being attracted by its protons. This interplay of forces results in some atoms joining and forming bonds. The two main types of bonds formed between atoms are ionic and covalent. Covalent bond is formed when valence electrons are shared between atoms. An ionic bond is formed when one or more electrons are completely transferred from one atom to another. Let's take a look at the simplest of covalent bonds, the bonding between two hydrogen atoms. Each atom of hydrogen contains a single electron. As the two atoms join together, they will share their electrons, creating a covalent bond. Halogens such as chlorine also form molecules through covalent bonding. In the case of a chlorine atom, there are 7 valence electrons. If two atoms of chlorine are joined together, they will share 2 electrons and form a covalent bond. Similarly, hydrogen and chlorine atoms will form a hydrogen chloride molecule through covalent bonding. The single electron from the hydrogen atom and one of the 7 valence electrons from the chlorine atom will form the bond. A double covalent bond is also possible in diatomic molecules such as oxygen. 2 atoms of oxygen with 6 valence electrons will share 2 pairs of electrons and form a double covalent bond. If we look at a molecule of carbon dioxide, we can also see double covalent bonds. In this case, oxygen has 6 valence electrons and carbon has 4. The carbon will share 2 of its 4 electrons with one oxygen atom on one side and 2 additional electrons on the other side. This sharing of 4 electron pairs will result in 2 double covalent bonds in the carbon dioxide molecule. Summary: chemical compounds are formed by joining of 2 or more atoms. A covalent bond is formed when valence electrons are shared between atoms. A double covalent bond is formed when 2 pairs of electrons are shared between atoms.
Hydrocarbons are constituents of cell membranes, fossil fuels like petroleum, waxes like paraffin wax, and polymers like polyethylene. Hydrocarbons contain only carbon and hydrogen atoms. These atoms can combine in an infinite number of ways to produce millions of different compounds. Let's see how. Carbon atoms can bond covalently with hydrogen atoms and other carbon atoms by sharing electrons in a variety of ways. When 2 atoms share only one pair of electrons, a single bond is formed with each atom contributing a single electron to the bond. When 2 pairs of electrons are shared between 2 carbon atoms, a double bond is formed. When 3 pairs of electrons are shared between 2 carbon atoms, a triple bond is formed. For example, the methane molecule is made up of 1 carbon atom covalently bonded with 4 hydrogen atoms. Each of these 4 bonds are single bonds. That is, each bond is formed by sharing only 1 pair of electrons. Hydrocarbons, in which the carbon atoms form only single bonds with each other, are called saturated hydrocarbons. Hydrocarbons in which the carbon atoms form double or triple bonds with each other are called unsaturated hydrocarbons. All hydrocarbons formed by single bonds between carbon atoms such as methane, ethane, propane, etc. belong to a family of compounds known as alkanes. This is called a homologous series, in which a chain of carbon-hydrogen molecules formed with single bonds is built up progressively. Compounds of the same homologous series share the same suffix in their names. For example, methane, ethane, propane, butane, pentane, hexane, etc. They also have similar chemical properties. Alkanes are represented by the molecular formula as CnH2n plus 2, where N stands for the number of carbon atoms. Because they are formed by single bonds between atoms, alkanes are called saturated hydrocarbons. All hydrocarbons having at least one double bond between a pair of carbon atoms belong to a family of compounds known as alkenes. In the ethene molecule, the two carbon atoms share two pairs of electrons to form a double covalent bond. The hydrogen atoms are each linked to the carbon atom by a single bond. In total, there are 4 CH single bonds and 1 CC double bond. Alkenes form a homologous series and are represented by the molecular formula CnH2n, where N stands for the number of carbon atoms. Because they are formed by double bonds between atoms, alkenes are called unsaturated hydrocarbons. All hydrocarbons having at least one triple bond between a pair of carbon atoms belong to a family of compounds known as alkynes. Ethyne, propyne, butane, etc. are examples of some alkynes. In the ethyne or acetylene molecule, the two carbon atoms share 3 pairs of electrons to form a strong triple covalent bond. The hydrogen atoms are each linked to the carbon atom by a single bond. In total, there are 2 CH single bonds and 1 CC triple bond. Alkynes form a homologous series and are represented by the molecular formula CnH2n-2, where N stands for the number of carbon atoms. Because they are formed by triple bonds between atoms, alkynes are called unsaturated hydrocarbons. These unsaturated hydrocarbons are highly reactive and flammable. For example, a mixture of acetylene and oxygen is used in oxyacetylene welding and cutting. Thus, hydrocarbons can be classified into 2 types based on the number of bonds present between the atoms. Saturated hydrocarbons have a single bond between the atoms. Unsaturated hydrocarbons have either double or triple bond between the atoms. Saturated hydrocarbons are less reactive than unsaturated hydrocarbons. All alkanes such as methane are saturated hydrocarbons. Alkenes such as ethane and alkynes such as acetylene are unsaturated hydrocarbons.
Many important fuels are made up of hydrocarbons. Hydrocarbons are carbon compounds that contain only carbon and hydrogen. The carbon atoms may be linked by single, double, or triple bonds. Hydrocarbons that contain only single bonds between carbon atoms are called alkanes. For example, ethane has a single bond between the carbon atoms. Hydrocarbons that contain one or more double bonds between carbon atoms are called alkenes. For example, ethene has a double bond between the carbon atoms. Hydrocarbons that contain one or more triple bonds between carbon atoms are called alkynes. For example, acetylene has a triple bond between the carbon atoms. The carbon atoms in carbon compounds are arranged as straight chains, branch chains, or cyclic chains. Let's see how. The compounds in the alkane series are structured in the form of linear chains of carbon and hydrogen atoms. Here, the carbon atoms are linked to each other in the form of straight chains. The members of the series are named according to the number of carbon atoms they contain. For example, the smallest of the alkanes is methane. Methane is a primary component of household natural gas. The methane molecule contains 1 carbon and 4 hydrogen atoms. Ethane contains 2 carbon and 6 hydrogen atoms. Propane has 3 carbon and 8 hydrogen atoms. Butane has 4 carbon and 10 hydrogen atoms. Pentane has 5 carbon and 12 hydrogen atoms. And hexane has 6 carbon and 14 hydrogen atoms. Carbon compounds with the same formula but different structures are called structural isomers. These isomers arise due to branching in carbon chains. For example, the butane molecule is represented by the formula C4H10. Butane has 2 isomers. In one, the carbon atoms lie in a straight or linear chain, whereas in the other, the chain is branched. Simple branched alkanes often have a common name using a prefix to distinguish them from linear alkanes. For example, N-butane is formed in a linear chain and isobutane in a branched chain. In addition to straight and branched chains, some carbon compounds have a ring-like or cyclic structure. Here, the carbon atoms are linked to each other in the form of a ring-like structure. For such compounds, the prefix cyclo is added to their names. For example, cyclohexane is a saturated hydrocarbon with the carbon atoms arranged in a hexagonal ring. Similarly, cyclopentane has carbon atoms arranged in a pentagon-shaped ring. The carbon atoms in the industrial solvent benzene are arranged in a symmetrical ring with alternating single and double bonds between the carbon atoms. Some compounds are made up of combinations of rings and chains such as toluene, which is an important solvent, and naphthalene, used in mothballs. To conclude, hydrocarbons can have different structures depending on the bonds formed between the carbon atoms in the hydrocarbon. If the carbon atoms in a hydrocarbon are linked in a linear manner, we get straight chain hydrocarbons. If the carbon atoms are linked in a branched manner, we get branched chain hydrocarbons. And finally, if the carbon atoms are linked in a cyclic manner, we get cyclic hydrocarbons. Besides, carbon atoms in a hydrocarbon could also form combinations of rings and chains to give complex hydrocarbons.
IUPAC nomenclature. Linear alkane nomenclature. The International Union of Pure and Applied Chemistry, founded in 1919, established a worldwide set of rules for naming compounds. Alkanes are hydrocarbons, meaning they can contain only the elements of hydrogen and carbon. Alkane nomenclature uses a system of prefixes to identify the number of carbons in the longest continuous chain.
The "ane" ending in the name pentane indicates that all of the carbon-carbon bonds in the molecule are single bonds. The simplest alkane has only one carbon. It is named methane. The next alkane with 2 carbons is named ethane. The alkane with 3 carbons is named propane. The alkane with 4 carbon atoms in a chain is named butane. Sometimes alkanes are drawn with lines that represent the bonds between carbon atoms. This format emphasizes the carbon chain of the molecule. Pentane is the name of the alkane with 5 carbon atoms side by side. Here, it is shown in both formats. Hexane, the next alkane, has 6 carbon atoms in a chain. The alkane with 7 carbons in a row is named heptane. The molecule octane has 8 carbons side by side in a chain. The alkane with 9 carbons in a continuous chain is named nonane. Decane is the name given the alkane with 10 carbons side by side. Knowing the names of the first 10 alkanes is the basic for the entire IUPAC nomenclature system for organic molecules. Summary. In this session, we have learned how to name and identify the first 10 alkanes. The "ane" ending in the names of alkanes indicates that all of the carbon-carbon bonds in the molecules are single bonds. IUPAC nomenclature of branched alkanes. Hydrocarbons contain only hydrogen and carbon. A saturated hydrocarbon is a hydrocarbon in which all the carbon-carbon bonds are single bonds. Such saturated hydrocarbons are called alkanes. Each carbon atom forms single covalent bonds with hydrogen. Naming organic compounds is called the IUPAC system. The initials signify the International Union of Pure and Applied Chemistry, which is an international body to set standards for chemists. In the IUPAC system, naming the branched chain alkane is based on the longest continuous chain of carbon atoms in the structure. The branched chain alkanes are named according to a sequence of steps. Look at this simple example. Identify the longest continuous chain of carbon atoms in the structure. There are 2 possible ways to number the longest chain, from left to right and from right to left. In this example, in either instance, the longest chain has 3 carbon atoms. Therefore, the prefix will be prop. There are only single bonds between all the carbon atoms. Adding the suffix "ane" makes the name of the longest carbon chain and called propane. Name the branches or side chains. The branch or side chain in this molecule is CH3. It is methyl group. Number the longest carbon chain so that the branch or side chain is attached to the carbon atom with the lowest number. In this example, the branch is at the second carbon in any instance. Start the name with the position of the branch, which is 2, and the name of the branch, which is methyl. The beginning of the molecule's name will be 2-methyl. The complete name of the branched chain alkane is 2-methylpropane. Summary. The IUPAC nomenclature of branched alkanes starts with naming the longest carbon chain. Next, the name and the location of the branch are identified. Combining the names results in the complete name of the branched chain alkanes.
The flame we see when we strike a match is the result of combustion or burning. Combustion is the burning of a substance in the presence of oxygen, accompanied by the release of energy in the form of heat or light or both. All carbon compounds burn in oxygen to produce carbon dioxide, heat and light. For example, methane burns in oxygen to give carbon dioxide, water, heat and light. A matchstick catches fire only when it is rubbed against a surface. The friction produced by rubbing generates heat. Once the ignition temperature is reached, the matchstick begins to burn. Similarly, simply mixing methane with air will not cause methane to burn. Some energy is needed to ensure that the fuel reaches its ignition temperature, which in turn will trigger the combustion reaction. This ignition is provided initially by another flame, a spark or a hot surface. The burning of methane in air is called an exothermic reaction because energy is released in the form of heat and light. Have you ever wondered why a candle burns with a yellow sooty flame and why the cooking gas burns with a clean blue flame? This happens due to partial combustion and complete combustion respectively. Let us now look at what is meant by partial combustion and complete combustion. Complete combustion occurs when the carbon compound burns completely in oxygen to produce carbon dioxide and water as byproducts. Cooking gas is made up of saturated hydrocarbons. These hydrocarbons burn completely to produce a clean blue flame. Incomplete or partial combustion occurs when there isn't enough oxygen and the fuel does not react completely with the oxygen. Candle is made up of unsaturated hydrocarbons. These hydrocarbons do not burn completely and will therefore produce a yellow sooty flame that contains unburnt carbon particles. By limiting the supply of air, even saturated hydrocarbons will burn with a yellow sooty flame due to partial combustion. Partial combustion produces soot or carbon and carbon monoxide. You have just learnt about the properties exhibited by carbon compounds on combustion. Can you answer these questions? What is combustion? What is an exothermic reaction? What kind of a flame is produced when unsaturated hydrocarbons are burnt? What happens to the flame on a gas burner when the supply of air is limited? Ethanol or ethyl alcohol is an active ingredient in beer, wine, and alcoholic beverages. It is used as an alternative fuel and a fuel additive in ethanol-blended fuels. Ethanol adds oxygen to petrol, helping it burn completely and thereby reducing toxic exhaust emissions. Ethanol is also used in varnishes and perfumes and as a preservative for biological specimens, in drugs and medicines, in essences and flavorings, and as a disinfectant. The molecular formula of ethanol is C2H5OH. Ethanol consists of two carbon atoms bonded to each other by covalent bonds. These carbon atoms are further bonded to 5 hydrogen atoms and a hydroxyl group by covalent bonds. Ethanol is made by fermenting and then distilling starch or sugar crops such as sugarcane, maize, and wheat and other grains, or even biomass such as corn stalks, fruit and vegetable waste. Ethanol is a liquid at room temperature. Its melting point is 156 degrees Kelvin and its boiling point is 351 degrees Kelvin. It is a good solvent and is soluble in water in all proportions. It is therefore used in tincture iodine, cough syrups, and tonics. Consumption of dilute ethanol can cause drunkenness, and consumption of pure ethanol can be lethal. Ethanol burns in air with a blue flame to form carbon dioxide and water. Ethanol reacts with active metals to form the metal ethoxide and hydrogen. For example, when a small piece of sodium is dropped into a test tube of ethanol, at room temperature, the sodium reacts with the ethanol to give off hydrogen bubbles and a white solid called sodium ethoxide is left behind. When ethanol vapor is passed over heated aluminium oxide powder or concentrated sulfuric acid, ethanol gets dehydrated and forms ethene and water vapor. Aluminium oxide and sulfuric acid serve as a catalyst in this reaction. The dehydration of ethanol is a reversible process. Ethanol can be reobtained by adding steam to ethene. Ethanoic acid is used in the preparation of vinegar that is used as a preservative in pickles. Ethanoic acid is used in the preparation of esters. Esters are sweet-smelling substances that are used in making perfumes and as flavoring agents. Ethanoic acid is also used in the preparation of soaps. The molecular formula of ethanoic acid is CH3COOH. Ethanoic acid consists of 2 carbon atoms bonded to 3 hydrogen atoms, an oxygen atom, and a hydroxyl group by covalent bonds. Ethanoic acid is produced by the oxidation of ethanol. Ethanoic acid is a colorless liquid that has a pungent odor. It is commonly known as acetic acid and belongs to a group of weak acids known as carboxylic acids. The melting point of ethanoic acid is 290 degrees Kelvin and its boiling point is 391 degrees Kelvin. A 5 to 8% solution of acetic acid in water is used to prepare vinegar that is used as a preservative in pickles. As it is a weak acid, it is not completely ionized in a solution. Ethanoic acid reacts with ethanol in the presence of an acid catalyst to give an ester. This reaction is known as esterification. Esters react in the presence of an acid to give back the alcohol and carboxylic acid. This is the reverse of the esterification reaction. However, esters react with a base to give the corresponding salt of the ester and alcohol. If the base is sodium hydroxide, the salt formed is sodium ethanoate. This reaction is known as saponification because it is used in the preparation of soap. Ethanoic acid turns blue litmus red and neutralizes alkalis to form salt and water. Ethanoic acid decomposes carbonates in an effervescent reaction to liberate carbon dioxide along with sodium acetate and water. Ethanoic acid also decomposes hydrogen carbonates in an effervescent reaction to liberate carbon dioxide along with sodium acetate and water. When ethanoic acid reacts with sodium carbonate or sodium hydrogen carbonate, a simple acid-base neutralization reaction occurs, resulting in the formation of a salt, water, and carbon dioxide.
Ethanoic acid. Ethanoic acid is a carboxylic acid and is commonly known as acetic acid. The molecular formula of acetic acid is CH3COOH. Ethanoic acid is a colorless liquid with sour taste and strong odor. It is miscible with water. When ethanoic acid is diluted with water, it becomes vinegar. Ethanoic acid reacts with the base sodium hydroxide to yield sodium acetate salt. Ethanoic acid reacts with alcohols to form esters. Ethanoic acid reacts with ethanol in the presence of concentrated sulfuric acid to produce ethyl acetate, which is an ester, and water. This reaction is called esterification. When ethyl ethanoate reacts with sodium hydroxide, ethanoic acid and ethanol will form. This process is used in making soaps, so it is called saponification. Ethanoic acid reacts with sodium carbonate to form sodium ethanoate, which is also referred to as sodium acetate, carbon dioxide, and water. Ethanoic acid reacts with sodium hydrogen carbonate, which is also called sodium carbonate, to form sodium acetate, carbon dioxide, and water. Ethanoic acid is used in making vinegar, which is used as preservative. It is used in the manufacture of acetone, esters, dyes, plastics, and pharmaceuticals. Summary: ethanoic acid is colorless liquid with sour taste and strong odor. Ethanoic acid reacts with base sodium hydroxide to yield sodium acetate salt. Ethanoic acid reacts with alcohols to form esters. Ethanoic acid is used in the manufacture of acetone, esters, dyes, plastics, and pharmaceuticals.
Esters. Esters are organic compounds which are derivatives of carboxylic acids. A carboxylic acid is an organic acid containing at least one carboxyl group, written as COOH. They contain a carbon atom that is bound to three other atoms. One is a single bond to a carbon atom. One is a single bond to an oxygen atom. And the other is a double bond to an oxygen atom. The singly bound oxygen atom will be bound to another carbon atom. The general structural formula for an ester is written as RCOOR', where R and R' are alkyl groups. In the case of ethyl acetate, R would be CH3CH2 and R' would be CH3. If we look at the structure of esters, we can see the carbonyl center will form a 120-degree angle with carbon-carbon-oxygen bonds and oxygen-carbon-oxygen bonds. The most common ester is ethyl ethanoate. In this case, the hydrogen in the COOH group has been replaced by an ethyl group. The structural formula for ethyl ethanoate is CH3COOCH2CH3. Other esters include methyl butanoate, ethyl propanoate, propyl methanoate, and propyl ethanoate. Esters can be prepared by esterification, a process during which carboxylic acids react with alcohols in the presence of hydrochloric acid. During esterification, the alkoxy or O-alkyl group in the alcohol will replace the hydroxyl group in the carboxylic acid. Esters having a low molecular weight are colorless and volatile liquids which produce the fragrance of flowers and flavor of fruits. Bananas, for example, contain isopentyl acetate, and pineapples contain ethyl butyrate. Fats and oils are esters of long-chain carboxylic acids and glycerol. Industrially, esters can be used in the preparation of plastics such as polyesters. Summary: esters are organic compounds which are derivatives of carboxylic acids. Esters are prepared by esterification, a process during which carboxylic acids react with alcohols in the presence of hydrochloric acid. Esters produce the fragrance of flowers and flavor of fruits. Esters are the components of fats, oils, and polyesters.
Esters are chemical compounds that have a pleasant, fruity odor. Esters are used in perfumes and food flavorings. Esterification is a reversible chemical reaction in which an alcohol like ethanol and a carboxylic acid like ethanoic acid react in the presence of an acid catalyst to produce ethyl ethanoate, an ester, which is also known as ethyl acetate. Ethyl ethanoate is formed by the combination of the ethyl group from ethanol and the ethanoate group from ethanoic acid. Ethyl acetate is used in glues and nail polish removers, as a solvent to clean circuit boards, and in the process of decaffeination of coffee beans and tea leaves. Esters are also used in the synthesis of polymers. For example, polyesters are a type of polymer and are used extensively to produce fabrics, bottles, films, etc. Let us now see how esters are prepared in the laboratory. Use a pipette to measure 10 ml of ethanol and pour it into a clean 250 ml Erlenmeyer flask. Next, add 10 ml of acetic acid. Then, carefully add a few drops of sulfuric acid as a catalyst. Swirl the flask to mix the contents. Stopper the flask firmly with a cork stopper and glass tubing. Heat the flask in a water bath on a hot plate. The contents should be kept just below their boiling point. Heat for 10 minutes. Then remove the flask and allow it to cool. You will be able to smell the ester produced by the reaction of ethanol with acetic acid. The ester can be separated from the mixture by distillation. Ester has a lower boiling point, and we distill out first. As little children, we were given baths with gentle soaps. As youths and adults, we pick fragrant soaps and shampoos of our choice. How did we come to have such a wide choice? The earliest recorded history of a soap-like material goes as far back as 2800 BC to ancient Babylon. Later, the Egyptians created a combination of animal and vegetable oils and alkaline salts. The result? A soap-like substance for bathing. Commercial soap making received a boost in the 19th century after the Belgian chemist Ernest Solvay developed the ammonia soda process for producing soda ash or sodium carbonate, which is used because it is cheaper than lye or sodium hydroxide. Today, due to commercial production, we have a wide variety of soaps, shampoos, and even detergents for washing clothes available to us. These cleansing agents have become a part of everyday life. So, what goes into the making of these soaps and detergents? Industrial soap making has 4 main steps: saponification, removal of glycerin, purification of soap, finishing. Saponification involves the combination of fats and oils with alkalis, which is heated to produce glycerin and soap. Sapo means soap in Latin. The fats and oils used for soap making are called triglycerides. Most soaps are made from vegetable oils such as olive oil, palm oil, and coconut oil. Some soaps are made from animal fats, tallows. The common alkalis used in soap making are sodium hydroxide or NaOH and potassium hydroxide or KOH. When the alkali is sodium hydroxide, a sodium soap is formed, which is hard. When the alkali is potassium hydroxide, a potassium soap is formed, which is softer. Once saponification is complete, some of the glycerine is removed, while some is left in the soap to keep it soft. Then, the soap is purified by neutralizing the sodium hydroxide with a weak acid. Any remaining water is also removed. Finally, colors, fragrances, and preservatives are added to the soap, and the soap is shaped into bars. If you've ever tried washing dirty clothes or greasy dishes in plain water, you'll know that it doesn't get rid of the dirt. That's because grease and dirt are organic in nature and insoluble in water. When soap is dissolved in water, the soap molecules act as dirt removers. Soap molecules are made up of long chains of carbon and hydrogen atoms. At one end of the chain is a configuration of atoms which are hydrophilic or dissolve in water. The other end is hydrophobic or does not dissolve in water, but dissolves in hydrocarbons or oil. When washing with soap, the hydrophobic ends of the soap molecules get attached to the dirt and grease particles. The particles of grease or dirt are loosened by the soap molecules around them and form a ball-like structure called a micelle. The hydrophilic head remains on the outside, and the hydrophobic tails remain on the inside of the micelles. These micelles remain suspended in water and are washed away when rinsed with water, carrying the dirt particles with them. Your dirty clothes or greasy dishes now come out clean.